Hello everyone, welcome back. In this lesson, we're going to look at creating a model for the relationship between two quantitative variables. This is known as linear regression. And so we want to make predictions on the response variable based on some value of the explanatory variable. So if a scattered plot shows a linear association between these two variables, then what we could do is use a straight line to fit the data. So recall from algebra that the equation of a line is given by y equals mx plus b, where m is the slope of the line and b is the y-intercept. Now for our course, we're going to use this notation. So we have y hat is equal to b1x plus b naught. So y hat is going to be the predicted value, b1 is going to be the slope, and b naught is the y-intercept. Now if we're given a scatter plot, then there are many different lines that can pass through the data. Now which line do we pick that will best fit the scatter plot? Now to answer that question, we're going to look at defining what is called the residual, which is the difference between the observed value and its predicted value, and it will represent the vertical distance from the observed value and the line. Now let's suppose we have this scatter plot here, and this is the line that passes through the data. Now if we're given some observation, we'll call it y, then the line will predict a certain value for this particular explanatory variable. Okay, we'll call the predicted value y hat, and now the vertical distance between the observed value and the value that is predicted by the line is called the residual. Now the line that will best fit the data is called the least squares regression line, or the line of best fit, and is the one that minimizes the squared residuals. Okay, so why do we want to minimize the squared residuals? Well, if we were to sum up the residuals, then they will always add up to 0. Just like when we sum up the deviations for a given data set, the sum of the deviations will always equal 0. So we're going to look at minimizing the squared residuals. So now the line that minimizes the squared residuals will have certain coefficients given by these formulas. Now these coefficients are calculated by using a bit of calculus. And so the slope of the line, so b1, is going to be r times sy over sx, where r is the correlation coefficient and sy and sx are the standard deviations of the x and the y variables. Now the y-intercept, so b naught, is given by y bar minus b1 times x bar, where y bar and x bar are the means of the x and the y variables. So now the slope is expressed in y units over x units, and it will tell us how the y variable will change for every 1 unit change in the x variable. So that is the interpretation of the slope. Now the intercept will tell us the value of y when the x variable is equal to 0. Now in some cases, this may not be meaningful to interpret, and so predicting the value at x may not give us very useful information. All right. So let's have a look at an example here. So here we have the altitudes, which are measured in thousands of feet, and the outside air temperatures measured in degrees Fahrenheit, recorded during a flight from New Orleans to Atlanta. So here are the two quantitative variables. We have the altitude and the temperature. So we obtain the following statistics So x is going to be the altitude. This is the explanatory variable. And y is going to be the response variable, which is the outside air temperatures. So we're given the means and the standard deviations of both variables, as well as the correlation coefficient. So if we have a look at the scatter plot, here are the plots of each of these pairs, as well as the line of best fit. So let's first find the equation of the regression line. Okay, so to find the equation of the regression line, what we need is the slope of the line as well as the y-intercept. So to find the slope of the line, we take the correlation coefficient multiplied by the standard deviation y divided by the standard deviation in x. So we're given that the correlation coefficient is negative 0.997, and the standard deviation of the y variable is 42.221. Oops. And the standard deviation of the x variable is 11.423. So this will give us a slope of negative 3.685. And now we can use this to calculate the y-intercept. So the y-intercept is given as y bar minus b1 times x bar. So we take the average of the y variable, which is negative 1.714, minus the slope, which is negative 3.685, times the average in the x variable, which is 20.143. So this will give us a y-intercept of 72.514. And so the equation of the linear regression line is given by y hat, which is equal to negative 3.685 times x plus 72.514. Okay, so now let's use this line to predict the temperature at 20,000 feet. Now here, we're given that the x variable, which is the altitude, is measured in thousands of feet. Okay, so we do have to pay attention to the units of our variables. Now, if we want to predict the temperature at 20,000 feet, then the x variable is going to be equal to 20. Okay, so this is because the altitude is measured in thousands of feet. So if we want to predict the temperature at 20,000 feet, we're going to let x be equal to 20 in the linear regression equation. And so the predicted temperature is going to be negative 3.685 times 20 plus 72.514. And this will be negative 1.186 degrees Fahrenheit. All right, so now what is the interpretation of the slope? Okay, so we're given that the slope is negative 3.685. So the slope will tell us the change in the response variable for every 1 unit change in the x variable. Okay, so here x is measured in thousands of feet. So for every 1 unit change in altitude will give us a certain change in the response variable. Okay, so an increase of 1,000 feet in altitude. Okay, so remember that the units for the x variable is in thousands of feet. So for 1 unit change, so for every 1,000 feet increase in the altitude, this will be associated with a decrease in temperature by 3.685 degrees Fahrenheit. Now it is a decrease in temperature because the slope is negative. All right, so let's have a look at another example. So here we have a table of the calories and the total fat content in grams in a sample of Tim Hortons donuts and cookies. Okay, so here we have the following statistics. So x is going to be the amount of fat content, and y is going to be the calories. So here we have the mean and the standard deviations of both of these variables, as well as the correlation coefficient. So here's a scatter plot of the data, as well as the line of best fit. So let's first find the equation of this line. All right, so again, the equation of the line is b1x plus b0. b1 is r times the standard deviation in y over the standard deviation in x. So the correlation coefficient is 0.895. The standard deviation of the y variable is 51.4. The standard deviation of the x variable is 5.15. So this will give us a slope of 8.933. And now we can use this to calculate the y-intercept. So the y-intercept is y bar minus b1 times x bar. So the average of y is 269.2. b1 was 8.933. And x bar is 14.00. And so the y-intercept is going to be 144.138. So the equation of the regression line is 8.933 times x plus 144.138. All right, so now what does the slope of the regression line show? All right, so what is the interpretation of the slope? So the slope was given as 8.933, And so for every 1 unit increase of the x variable, it's going to be associated with an increase of the y variable. So what we have here is that the x variable is the amount of fat content, which is measured in grams. And so for every 1 gram increase of fat content is associated with an increase in calories by 8.933. Okay, and calories, well, they're measured in calories. Okay. So now in the next example, here we're given some statistics that were obtained from collected data. Okay, so here we're given the mean and standard deviation of the x variable, the mean and standard deviation of the y variable, as well as the y-intercept of the regression line. So now we can use this information to find the equation of the regression line. Okay. So again, recall that the equation of the regression line is b1x plus b naught. Oops. Now to find the slope of the line, we're going to take the correlation coefficient times the standard deviation in y over the standard deviation in x. Now for this question, we're not given the correlation coefficient. So we're unable to determine the slope of the regression line using this formula. So now we need to determine the slope of the regression line using another formula. So recall that the y-intercept is given as y bar minus b1 times x bar. So we can rearrange and solve for b1, which will give us the slope of the line. Okay, so if we were to add b1 x bar to both sides, we get b naught plus b1 x bar is equal to y bar. And then we will subtract b naught on both sides, which gives us b1 x bar is equal to y bar minus b naught. And so b1 is y bar minus b naught over x bar. So the slope of the line is given as 474.4 minus 11.84 divided by 4968. And so the slope of the line is 0.093. And so this tells us that the equation of the regression line is 0.093 times x plus 11.84. Yep. Okay, so now that we have the slope of the line, we can use this to determine the correlation coefficient. So if you look at the first slope formula, we have b1 is equal to the standard deviation of y over the standard deviation and x. Then we can rearrange and solve for the correlation coefficient. So if we were to multiply both sides by the standard deviation of x, and then divide by the standard deviation of y, then we get r. So we have 0.093 times standard deviation of x, which is 3110, divided by the standard deviation in y, which is 296.0. And this will give us 0.978. All right, so now the next thing we'll talk about is the coefficient of determination. So if we go back to our earlier examples where we looked at the Tim Hortons items, what we found was the equation of the regression line given as follows. And the average amount of calories for all of the items was 269.2. And if we had a look at one particular item, for example, the sour cream glazed donut, what we found was 17 grams of fat with 340 calories. So now if we were to use the linear regression line to predict the amount of calories for 17 grams, what we would obtain is 296 calories. Okay, so let's have a look at a diagram of the different values that we obtain. So here, this red line here is the line of best fit, so the linear regression line. And the sour glazed donut here is the observed value. So we had 17 grams of fat with 340 calories. What the line predicts is going to be a value of 296 grams. Now this blue line down here is the average calories for all of the items. And we found that the average was 269.2. So we can use this diagram to look at the different deviations for each of these values. So if we have a look at the difference between the observed value from the sour cream or glazed donut to the average amount of calories, this is called a total deviation. So this is given as y minus y bar. Now, the total deviation can be separated into two other deviations. One is called the explained deviation. So the deviation that is between the average amount and the predicted calories, as well as the unexplained deviation, which is the difference between the observed value and the line. So here we have the relationship between these for any individual observation. So the total deviation is the sum of the explained deviation and the unexplained deviation. So the above expression involves the deviations from the mean. And if we were to sum up the squares of the deviations, what we obtain is the amount of variation. Okay, recall that the variation is the squared deviations. So the total deviation is going to be the sum of y minus y bar squared. The explained variation is going to be the difference between the predicted value, which is y hat, minus the average value, which is y bar. And then we have the unexplained variation, which is the difference between the observed value and the predicted value. So the total variation will satisfy this identity here. And it says that the total variation is the sum of the squares of the total deviation values. So the explained variation is the sum of the squares of the explained deviation values, and the unexplained variation is the sum of the squares of the unexplained deviation values. So we can use these variations to define the coefficient of determination, which is denoted as r squared, and it is the proportion of the variation in y that is explained by the regression line. And it is calculated as follows. So we take the ratio of the explained variation over the total variation. And it will tell us the proportion of variation in the response variable that can be explained by the explanatory variable. So we'll have a look at the coefficient of determination for the Tim Hortons example that we talked about earlier. Okay, so let's have a look at calculating the coefficient of determination. Oops. So if you recall from our Tim Hortons example, the correlation coefficient was given by 0.895. And so to calculate the coefficient of determination, we simply take r and square it. So we have 0.895 squared, which is 0.801. So our coefficient of determination is 0.801. So what is the meaning of the coefficient of determination? Well, the coefficient of determination says that 80.1% of the total variation in the amount of calories can be explained by the explanatory variable, which is the amount of fat content. Okay, so 80.1% of the total variation is explained by the amount of fat content. Now the remaining 19.9% of the total variation can be explained by other factors. For example, carbohydrates or sugars can explain the other variations in calories. All right. So now the last thing we'll talk about is interpolation and extrapolation. When we use the linear regression line to predict values of the response variable, then the range of the x variable should only be within the values of the observed data. So whenever we predict values within the range of our data, then this is called interpolation. And if we predict values outside the range of the observed values, then this is called extrapolation. Now, while the relationship may be linear over the range of the values that we observe, there is no guarantee that this trend will continue. So as an example, here is a scatter plot which shows oil prices between 1971 and 1982. So here's the scatter plot and the linear regression line. It appears to look linear within this range. Now, the model will predict the oil prices will increase on average by about $6.75 per year. However, if we look at the next scatter plot, what we see is an average decrease of nearly $5 per year between 1981 and 1990. So here what we have is a decrease in our oil prices rather than an increase. So we should only use our linear regression model to predict values within our range and not outside of our data.